All right. Good evening, everyone, and welcome to what is hopefully the first in a series of our Tuesday night presentation events. As you know, it's difficult to work a long presentation into our virtual meetings, or else we'd be running till midnight. So we decided to separate it out and do separate little events for that. And as part of our first one here, we've invited Don Kane WB2BEZ to talk to us tonight. Don has been a licensed ham for almost 50 years. He's an ARRL Life member, registered professional engineer in the state of New York with over 40 years of engineering experience, including product safety evaluation, electric utility substation and plant engineering, design and manufacture of diesel-powered generators, including controls and switchgear, rail transit, rolling stock and infrastructure engineering, and electrical construction and HVAC. Tonight's talk is going to present an overview of grounding and bonding as applied to the typical amateur radio installation with regards to power, lightning protection, and RF or antenna grounding. And with that, I give you Don Kane, and I'm going to mute.
Thank you. Let me just get the, I guess I got to share. Let me get the PowerPoint up here. Okay. Is that working?
Negative.
Negative. Okay, let's see. Share screen. Okay, here we go. Now it's working, right?
Yep, you're good.
Okay. Yeah, grounding is a relatively simple concept, and it's usually screwed up in the application due to many times conditions where ground electrodes are located, where the equipment's located, and so forth. But tonight I want to just really touch on the primary points to keep in mind when you want to get into grounding, when you have antennas and radio equipment that you want to protect as well as yourself. And it's a topic that you can actually, although it's simple in concept, you can really go down the rabbit hole doing research and studying about it, because there's a lot of little concerns along the way that you want to be careful for. We'll just hit the high points, which are primarily grounding versus bonding, the function of grounding and bonding, and we'll touch on lightning protection, which can be a whole topic unto itself, and varies depending on what kind of protection you're going to provide. You know, typically for your home station is not going to be the same as a broadcast station where they have many times the dollar value of equipment, and specific requirements for ham stations, especially as called out in the National Electrical Code. Some definitions, and I referenced the 2017 National Electrical Code because New York's state, that's the current adopted code, even though there is a 2020 version out. They're always an edition or so behind. Basically, ground is the earth, and grounding is being connected to the ground or earth. Simple, but just something to keep in mind. Bonding, on the other hand, it's when you connect two or more items to establish electrical continuity and conductivity. You can have equipment bonded together that's not grounded. You can have equipment that's grounded and not bonded. Ideally, you want both. The reason we ground voltage stabilization is from the utility viewpoint. It provides a more stable supply. Some European countries have ungrounded systems. In the United States, we have grounded systems referencing earth ground for the power coming into the house. Grounding provides an effective ground fault current path for under fault conditions, which permits operation of protective devices. And lightning protection. Now, most of the lightning protection that we'll have really protects you against indirect stroke or strike to the antenna. If you get a direct hit, you have very little chance of most antennas and feed lines surviving. But if you're careful in your installation, you'll be able to prevent additional damage to your house, keep the electricity outside. What won't grounding do? It won't prevent electrocution, and electrocution is fatal. Many times it's misused in the news and things like that. So they say someone was electrocuted and is recovering. You're electrocuted, you're toast. Ground fault protection will protect against electrocution. And the ground fault circuit interrupters that you typically have in your house, they do not require a connection to ground to function. It's purely a differential device that's looking at the gazouta and the gazinta, and when they're not the same, it trips. There are codes that require certain degrees of grounding. New York State has codes, New York City has codes. The NFPA 70, which is the National Electrical Code, has probably the largest section in that code is on grounding. And local codes. So each town and village may have their own requirements, especially if you have towers. The important materials that you'll be involved with grounding will be your electrodes, the conductors, and the terminations. And the goal of all this is to have equal potential bonding and a single point ground. And we'll talk more about single point ground shortly. It doesn't mean that you have to run home runs back to one ground point. It just means you don't want any equipment that's in proximity to each other to be connected to a different part of the grounding chain. You don't want any potential difference. You don't want any series connections. And if you do it right, it results in to minimize any of the potential differences. Remember, if you have your coax coming in from a tower to your rig, you have the shield, and many people will say, well, I don't want to bond the tower to the rest of the ground system. Don't need to, it's too far away. You still have now a source of potential coming in, and you have in the same equipment, you're going to have your green wire, your equipment grounding conductor from your house supply, and they're going to be at different potentials if there's a lightning strike or an electrical fault. So you really want to minimize that by bonding things together. And this had to come up with I've used this before mainly for buildings, but it applies because many people in apartments, they say, well, how can I have a single point ground? The theory is you can have it grouped into adjacent equipment. So here's system A, you have several pieces of equipment or other systems, but then they all tie together, and then it all goes down from all these other systems to a main ground plate, which then gets connected to the earth electrode system. Incidentally, a building frame, a metal frame, is considered an extension of the ground electrode conductor. So you can use that to tie things together if you're in a building with that construction or an office building. The importance of grounding is the various levels of tolerance to electric current. Charles Dalzell, who also was the father of the ground fault circuit interrupter, did many studies, found differences due to weight, and there's overlap between the reactions due to the weight of people. He tabulated, he did it, broke it down by male, female, DC, 60 hertz, 10 kilohertz. But a better illustration would be presenting it this way, because if you look at it, you'll see that the maximum harmless for a person who's 160 pounds is going to be at the painful shock level for someone who's only 100 pounds. So one of the reasons why the Class A GFCIs that you have in your house have a 4 milliamp to 6 milliamp trip range. They have to trip anything over 6 and stay connected anything under 4 milliamps. But You will with a ground fault circuit interrupter. If you have a fault and you're part of the circuit, you're going to feel a tingle. But the idea is it trips out the supply before it can do any damage and get into this maximum let go level or the fibrillation level, which will do you in. The degrees of grounding, you can have your outbuilding with a single ground. You can have ground grids in the soil. It all depends on what you're trying to protect and how much money you want to spend. If you have $50 worth of equipment, you're not going to spend $50,000 to put in a system to protect it. You'll just consider it a consumable. If you get into refineries and things like that, where they have a real problem, if there's any arcing or potential differences, they have very elaborate grounding systems with ground grids and so forth, as do electrical substations. And where these voltage inputs come from, it can be lightning strokes to power lines and comm lines. It can be strikes to the structure. There can be electrical faults. You can have a primary distribution wire fall on the secondary distribution, where all of a sudden, you're going to see this spike, and there will be a spike even on the secondary side of the transformer that can be significant when it gets to your house. Outside your structure, you have the antenna, the tower, the building itself, in some cases, if the metal building, any close by metal objects, other metal buildings, fences and the like, they're all of concern. Then you have your grounding field or electrodes, the rods and connections. These are all part of the outside concern. What's really key is you want to make sure for every conductive path into your house, whether it's your antenna, power, telephone, data, fiber cables, unless they're full dielectric fiber, they may have a metallic component inside. So you want to eliminate any path that will easily provide a way for any surges to come into your structure. And the so-called intersystem bonding device, this is one example that's called for in some of the code requirements, where you connect this device to your ground electroconductor, and then you can tie all your other systems to the other ports on the bar. Installed, it would look something like this on a house, and with the cover off. Okay. Something just happened. Okay. Oh, it's never happened before. Okay. Let's go back. Sorry about that. Something, the computer went wacko on me. Okay, so just make sure I got everything. The ground electrodes are typically ground rods of what we'll come across in an amateur installation or your house wiring. Conductors, your ground electroconductor, your bonding conductors. We'll talk a little about the flat conductor versus round conductors. In general, you'll hear a lot of people swear by flat conductors at lower reactance, which is all true. But the key point is, unless you have an appropriate connector that can terminate it to where it's being connected, if you have to crunch it up, you've basically lost a lot of that benefit. And anytime you have to take a sharp turn or get a bend in it or a nick, it can reduce the so-called or typical benefit that you're looking for. So usually solid and stranded copper conductors are what is the norm. Clamps, attachments, wells, terminations, very important that they be intended for the use. I've seen very expensive installations where people attach the ground electrode conductor to a tower leg with a hose clamp, and that's not going to do very much in case there's a serious fault or lightning strike. Connections, I can't stress enough. It's all about the connections, and you want to make your grounding connection and bonding connection at the building entry. You want to take it off the low point if it's a tower, not halfway up. Your ground rods typically, you'll have a listed clamp meant for ground contact, 8-foot rods and so forth. This is what you'll typically see. This is not a great example because of the sharp bends in the ground electrode conductor, which is something you want to avoid. But these are the acorn type nuts. Typically, you'll see with a ground rod, and most of them are only meant to be used with one conductor, not multiple. There are methods to test for the ground resistance, the fall of potential method. Typically, as hams, we don't get involved with that unless you have a very, very critical application where you're looking to get a super low ground resistance from your ground electrode system. One of the problems is the resistivity of soils varies all over the place from low to high, depending on what it is. Sand, very, very high resistance. Down near the shore, near the beach on the south shore of Long Island, where I live, it's like sticking into a bunch of glass beads. It's very, very much not a good conductor. Other ground electrodes, you will see metal water pipes, which are fewer and fewer these days. If it has 10 feet of earth contact, only good coming into your house if the connection is 5 feet or less from the entrance into the building, because you don't want someone further down the line to put some plastic pipe in between and you lose your continuity. Certain metal building frames, and again, this is more for a commercial type application, but there's requirements for the contact with concrete or the mounting bolts having to be tied in with either a concrete based electrode or steel in the concrete. UFA grounds, or the concrete enclosed electrode, you will many times see, and it's used a lot where a house is being built and they'll embed either the rebar or copper conductors in the footing and then bring a conductor up. It forms a very effective ground electrode as long as there's no vapor barrier or anything. The concrete has to be in direct contact with the concrete. It's going to be with the dirt, the soil, and you need minimum 2 inches of concrete around the conductive part, whether it's rebar or copper. If it's copper or galvanized coated material, 20 feet or more, 20 feet of 4-gauge copper wire. Rebar ties are considered acceptable for tying the rebars together, even if it's being used for the electrode, because the close proximity of the rebar, there's enough conductivity. Concrete is very conductive. This cannot be used if you have epoxy coated rebar because it's insulated. You don't get good contact, and without wasting too much time. And you have rod and pipe electrodes, pipe or conduit, stainless steel, galvanized steel, copper coated steel. The code requires 5/8 of an inch diameter, unless it's a listed ground rod, which is what most people would use. That may be less than 5/8 of an inch, as long as it's marked, it's listed 8 feet, and it has 8 feet in the ground in the soil contact. That would be acceptable. If you had a lot of plates, you could bury it. Depends whether it's copper or steel or copper. Copper, if you bury it in the ground, someone will probably dig it up and take it. Ground rods, which is what we'll mostly be familiar with, minimum of 8 feet in contact with the soil. So this means you have an 8-foot rod, it has to be totally buried. If you have a 10-foot rod, you can have part of it sticking out as long as it's 8 feet of actual soil contact. It can go in vertically. It can go in horizontally if it's at least 2.5 feet below the ground, the surface of the ground, and it can be angled up to 45 degrees. To comply with the code, you need 6 feet separation between ground electrodes, between the rods. Ideally, you want to have twice the length of the rod. So for 8-foot rods, you want to have 16 feet between them to get the most effective use of it. And the reasoning being, you have these shells of current that will form when it's passing electricity. And if you start putting more electrodes and they're close enough together, they really are sharing the same real estate. So you're not getting the full benefit. You're better off going deeper rather than with more closely spaced. The code only requires 25 ohms maximum ground resistance, which is pretty high, but suitable for most things that we would be doing unless you have, again, a very sensitive electronic installation. Some scientific installations have to have much lower ground resistance. It used to be you'd put in a ground rod and have to measure it, and if it wasn't 25 ohms, you put a second rod in, but didn't have to measure it again, which was kind of crazy, but the code is like that some days. And so now, after 2011, they said we'll just put in 2 ground rods because it's cheaper than having to bring some guy out to do any testing. Connections, again, it's all about the connections. If you look on any of the listed devices or sometimes in the packaging, you'll see markings that give the wire sizes. In some cases, it'll have for soil contact, direct burial. This is your typical acorn that you'd use to connect the electrode conductor to the electrode. This is an impact. This is like a hammered in mechanical wedging, swedging type terminal that's used for ground rods. It's not reversible, it's not reusable, but it's a quick and dirty way to make a connection. As long as you have one that's listed for direct soil contact. This is a cross section of a crimp connection. And just so you're aware that not all crimps are really what's called a gas tight connection. You have voids, which if you have them outside or in the ground will create problems from corrosion. This is the classic TMB hex crimp. This used to be many strands of copper. It's all crimped into one. It's barely discernible as separate conductors. This is a truly gas tight crimp. This is your best bet for grounding systems outside, is the exothermic welding or CAD weld is it's used almost generically, even though it's a trade name. It's a somewhat fiery process, but it's the only thing that the code recognizes as equivalent to an uninterrupted conductor. The classic CAD weld, you had a graphite mold, you had your charge that goes in there. There's a little disc, a ruptured disc, and then igniting material. You pour it in, light it, and send sparks all over. Now they do sell one-shots. These come, it's a little, I guess like a ceramic mold. You use it once, then you just knock it off and it's there. So on a per connection basis, these are a little more expensive, except if you're doing just a few, the cost of a graphite mold is excessive. Another key point in your grounding for your service ground, your ground in your house, is the main bonding jumper. What does it do? What does it look like? It can be a screw, a bus bar, a cable. And what it does basically is where your service enters your structure, your neutral and your ground are tied together. That's the only place where they should be tied together. If you have another panel in another room or in the basement or something or an outbuilding or garage, you need to keep the neutral and the ground separate and run all the wires back to the service panel where they're tied together. Again, you want one point where the neutral, and the ground are common. In the case of, most of the panels you look at, the service panels, you'll see this bar that goes across from the neutral to the ground bus. If you have a separate main disconnect, you have the neutral bar, you have the grounds coming in. This green screw grounds this to the case, and then that gets connected back here. So you have that single point. Or you may see a green screw like that ties the ground and the neutral bars together. That green screw in that application is one of the few times where the code calls out a specific color of the hardware. Any connection, any termination that's going to be relied upon requires a minimum of 2 threads or 2 threads engaged or secured with a nut that engage 2 threads or more. Some hardware is not acceptable for a reliable connection. Some is. It's a machine screw, a fine thread, a screw that has a tapping point on it and then has a fine machine screw head or thread. This is also acceptable. Tech screws are not acceptable. They're really almost like a glorified sheet metal screw. It has a drill point on, and the sheet metal screw definitely is not considered suitable hardware for terminating grounding or bonding terminations. If you have to run a grounding conductor, whether it's a ground electrode conductor or a bonding conductor by itself through steel conduit, you need to bond it to the conduit at both ends to prevent the inductive choking effect. So if you had something like this, you would have to, this is connected to this enclosure. This ring here connects the conduit there to this, and so forth down the line to where it comes out here to a pipe, and you have the termination here. This provides the bonding and then the connection to the ground. And a similar kind of arrangement there. It's very important though. I've seen people, they put a ground ring around an electric room, and then they put short pieces of conduit wherever there's a doorway so people don't step on the conductor, but they don't bond it. And they really defeat the whole purpose of having the ground ring. Also, you're putting the grounding conductor or the bonding conductor through a metal enclosure. You should have a fitting like that will again bond it to the enclosure. And this to prevent the inductive heating effect. Although, I mean, typically, unless you get up into hundreds of amps, you're not going to see a problem. But if you do have it like that level, it'll literally melt the sheet metal away if you don't have it bonded. This is the larger size if it's in conduit. This is an example of what not to do, although this is PVC conduit, so he doesn't need a bonding there, but he's put this big dog leg in the conductor, which again, you don't want bends, sharp bends. You want easy bends, keep it as straight as possible. This clamp, probably familiar with, this typical for connecting to pipes. It's not, unless it's identified as suitable for use with ground rods. And there are some that have like a double set of jaws in there. This is only for piping. If you have the reducing washers around a knockout that was too big, again, it has to be bonded around so you don't have any potential difference when that current starts to flow. Never leave excess cable. If you do have a fault, and if any of you ever seen A.B. Chance used to have some really nice short movies on faults in electrical utilities, and the safety grounds they use would whip around just tremendously. I mean, to the point where they're only good for one shot. Once they take a hit, they have to replace them. You have to bond around water meters and the like. So if the meter is removed, it doesn't create a discontinuity. This, unfortunately, it's an interesting example because there's gaskets on the flange connections, and unless they had provision for making sure the bolts are connecting to flange, it's isolated anyway, so it's not going to do very much. Just briefly, other piping, all metal piping which can become energized has to be bonded to the service ground, including gas piping. You cannot use gas piping as an electrode, as a ground electrode, but the gas piping, if it can be energized, has to be bonded to the service ground. Typically, if you have a gas appliance with a 3-wire plug, like a clothes dryer, that third wire, the grounding wire, will serve as the bonding connection. But if you don't have that, then you would have to have a bonding conductor. One of the problems, and I don't know, possibly upstate, it's more popular, the CSST piping, the corrugated stainless steel tubing used for gas. And that can create some problems. They've had with arcing when there's potential differences. And again, I'm not sure who your gas utility is there. Down here with National Grid, their blue book specifically gives the requirements when you have CSST in use, and what the grounding and bonding requirements are. And the key points are that it cannot be, the connection cannot be to the tubing itself or to the connector. There are some of the manufacturers of the tubing that do claim that the tubing has been tested with the connection to the nut, the hex nut, but unless your local or state rules permit it, or your utility permits it, it would not be possible, not be technically legit to use it. Okay, another area of concern or confusion sometimes, especially in older houses, you have type AC and type MC cable. They look very similar, armored cable. People most times generically will call it all BX, although BX was a trade name. But the old BX was definitely not suitable to use the armor as a grounding conductor. Current construction, the type AC cable, in addition to the white and the black conductor, they'll have usually aluminum conductor that's basically like a drain wire that bonds across the convolutions of the armor. And the armor then can be used as your equipment ground conductor. Type MC cable, on the other hand, in many cases doesn't have that, but it can. If it has it, it can be used for, the armor can be used for grounding. And again, in both cases with an appropriate connector. To identify them, the AC cable has paper wrap around the conductors. Type MC cable has a plastic wrap around the group of conductors. Okay, now we talk about the grounded conductor, and that's the neutral. It's the conductor that's intentionally grounded. The equipment grounding conductor, the green wire in the plug connects the non-current carrying metal parts to the grounded conductor, the ground electrode, or both. The AC cable, you don't bring that drain wire into the equipment box. It just gets folded back against the armor, and the connector goes over it. Usually people will put it through the connector and then loop it back so the connector doesn't fall off while they're installing it. The big difference is that your number of conductors, there's a limit in AC cable, no more than 4 conductors plus the equipment ground conductor, and the sizes. MC cable can have as many conductors as you can make it big enough to fit, and from small to extremely large in wire size. Okay, the grounded conductor or neutral, depending on what you may have, some older houses only had basically a 2-wire system. one side of it was grounded, and that would be your neutral. Typically, what we have today is a single phase, 3-wire system. The neutral ties to the midpoint of the secondary. You have 3 phases. You're going to have a Y system where the common point will be grounded, and that's again the neutral. In that case, there are 3-phase delta systems that are corner grounded, where one phase is ground connected, and then we have a delta system where you have half of one winding is tapped to give you a neutral. And typically for a 240 volt 3-phase system, this would give you 240 volts across phase to phase and 120 volts from phase to that neutral connection, if you're going from this phase or this phase to neutral. This, which is called the high leg, and typically you'll have orange insulation to identify it. You'll have much higher voltage. You'll actually have the 208 volts. You go phase to neutral there, so you would not use the high leg in combination with the neutral. Question people always bring up is which way to install the receptacle device. It doesn't matter. Code does not make a requirement for that. Everyone has their preferences, whether they want the ground pin up or down, depending on whether they're concerned with metal plates falling down on top of the plug if it's pulled out, or being able to support the plug. No requirement in the code at all for that. This is your typical house wiring. GFC requirements, and again, the basically almost every receptacle device in your house now has to have be on a GFCI circuit. There's a few exceptions, but bathrooms, garages, outdoors, crawl spaces, unfinished basements, kitchen, countertop surfaces 6 feet from the inside edge of the sink bowl, boat houses within 6 feet of outside edge of bathtub or shower stall, laundry areas. The GFCI, it's an electronic device, so it has a finite lifetime, has a bathtub curve. You will have either infant mortality or end of life. And some years back, they found out that a lot of them didn't work when they tested them. So now, and it's always been a requirement to test them every 6 months or so. Most people don't, but the current designs have fail-safe capability where if they're not functioning, they'll self-test and trip out, and it won't allow you to reset it until you replace it. Protection is also included on the newer model, so you cannot incorrectly wire it for the load side. 2 sets of terminals, so it not only protects that particular receptacle, but if you connect circuitry downstream of that receptacle, it'll provide ground fault protection for those also. And again, as I said, a grounding conductor, the ground equipment grounding conductor is not required for this to operate acceptably. In fact, one of the options the code gives you, if you have an old house with 2 wires circuit and a 2-blade receptacle, and you can't get a replacement receptacle for it, you can put a GFCI receptacle, and in the box with it, there's a little label that says not grounded. You put that on the receptacle on the plate, and it will give you ground fault protection. It will not give you ground protection, so that there's no grounding there. It doesn't magically create a ground, but it will give you ground fault protection. So if there's a fault, it'll trip out before you end up fried. Some circuit breakers they have a ground fault circuit breaker. Again, some of them have Class A ratings for the 4 to 6 milliamp trips. Some don't. So if you go that route, you should know what it is. And now, because the arc fault circuit interrupters is a whole new ball game, and just not that, because it's not really so much a grounding thing, but if any of you remember when the GFCIs were first going into use, there's a lot of trouble with tripping, especially in radio area. People had radio equipment that was sensitive to RF, they would trip out. And they finally, the manufacturers kind of resolved that. And it seems like some of them are relearning the process with the arc fault interrupters. So there are some, I know the league has done some work with some of the manufacturers, and I believe they have some stuff on their website as far as which equipment actually, which devices seem to work better in a high RF location. And why do we have that grounding conductor? Basically, if you don't have it and you have a fault, say to a motor enclosure or something, and you're standing on the concrete and you touch it, you're the ground path. Okay, if you have a grounded metal enclosure, and people always say, well, take the least, the easiest path or the least resistant path. No, the ground fault current will use all available paths. It's just that you form a voltage divider. So if the ground path that you provide is low impedance compared to your 300 to 500 ohm body impedance, then you'll just get a little tingle. Step potential, touch potentials are something to be aware of if you're in an area around electrical equipment or your tower. If there's say a lightning hit to your tower, there's going to be a gradient, a voltage gradient along the ground. And the best advice someone gave me years ago when I was at a seminar on substation grounding was, because he did a lot of work down in South America with some very, very primitive electrical utilities. He said, if all of a sudden, you find the hair on your arm is standing up, he says, lift 1 foot and hop away as fast as you can. Main things to keep in mind, additionally with grounding, you don't want to have it wired daisy chain style. So if you loosen something, you lose grounding for other parts. No disconnection issues. And you always want to provide equipotential bonding paths. Antennas and RF grounds. And again, this is all related to safety, not RF and antenna performance. Typically, many people will use smaller gauge wire for their ground planes or counterpoises, and that's fine from a antenna viewpoint in most cases. But if it's now it's all bonded together to your ground system, and if it's coming down from a tower or a very tall vertical, if there is a hit from lightning or nearby lightning stroke, that's all going to start to be part of the conductive system for the ground fault path. So you don't want it to be small enough where it's going to burn up. The other thing is for cross connections of radials, say at the base of a tower, RF wise, it probably doesn't affect performance very much, but what it does do is it equalizes the step potential in that area in case there's a lightning strike while you're in the area. So the distance, the voltage between the distance between your feet will be more tolerable. Hey, the question always comes, what does the code have to say about amateur radio installations? Transmitting and receiving, they don't have a lot, but in Chapter 8, they do have communication systems, and Article 810 covers amateur radio transmitting and receiving installations and also CB equipment. Covers transmitting and receiving equipment, the antennas, includes verticals and wire antennas. Article 810, the grounding of towers and masts, bonding to the power ground, separation of feed lines and power conductors, and antenna discharge units, which can be an iffy area because there are not always antenna discharge units that are listed, that are available, that will be suitable for amateur use. But most times, if you have coax that has a shield properly bonded to a ground due to one of the exceptions in the code, it's not going to be a problem. They do have minimum sizes for conductors and for antenna wires. It does prohibit mounting antenna masts to the service mast if you have a house where the electric service comes into a conduit sticking up past the roof. And anything that's going to be relied upon for protection and in your electrical system must be listed or approved for the use. Again, your local authority has the ability to approve or disapprove things. Protective devices, and it's best to have all your protective devices outside prior to where your cables and conductors enter your structure. And this goes for not just the antenna cables, but any control cables for your rotor, anything that is outside. You don't want to have a conductive path that can be present during an electrical event. And again, connection to a ground and bonding together. It all eventually has to get bonded to your service ground. Okay, you want everything all bonded together. The code has requirements for the type of material or lead-ins and for antennas, hard drawn copper and so forth. They make some exceptions if it's less than 35 feet. And you don't want it crossing over power conductors. Any splices should be mechanically secure. Solder is never considered a reliable mechanical securement method. So you always need some, it can be a crimp, it can be clamps, can be split bolts, but solder alone is not. Now, if you use like a Western Electric splice where it's mechanically secured by the double wrap and then soldered to give you electrical performance, that would be considered mechanically secure. But to use solder outdoors, unless you protect it from the elements, may create other problems with reactions to the rain, and especially if you're in an area that has anything in the air, whether it's an acid rain type situation. They masts and metal structures that are supporting antennas, the code requires them to be grounded. And unless the antenna and its supporting structure are within the so-called zone of protection defined by a 150-foot radius rolling sphere. And we'll get to the 100-foot rolling sphere in a minute, 150-foot rolling sphere. And again, there are requirements for bonding conductors and the ground electrode conductors. Without going through so much here, just materials, doesn't have to be insulated, has to be securely fastened. Wherever it's subject to mechanical contact, if it's where a lawnmower is going to go past or something, you need mechanical protection, either in Schedule 80 PVC or a little structure around it, but somewhere where it does not get destroyed. Putting it in the steel conduit, again, bond both ends and run it in as straight a line as possible. And again, connections, if you have that intersystem bonding termination. If not, there are, the building grounding electrode system, grounded metal water pipe, 5 feet where it comes in, so forth. And again, the code allows many things, but especially from an amateur point of view, where you have antennas and towers and things like that, where you want something that's really, really well protected, you're best, taking the trouble to get the bonding back to the service ground the way it should be. A bonding conductor or the ground electrode conductor can be run inside or outside of the house. Some people say, well, my station's over here and the ground electrodes are on the other side of the house. You can run it through your house if you want. And again, you don't have to run it in conduit. It might be a good idea just to protect it from mechanical damage. And many times what people will do is they'll have if they have the station on the other side of the house in that service, if you have a ground electrode system on that side and then bond that to your service ground on the other side, and everything is connected together. So yeah, that equal potential connection. A minimum of 10 gauge copper, 8 gauge aluminum, unless it's bonding between electrodes, and then a minimum 6 gauge copper is required. And keep in mind, these are all requirements in the code that probably never get looked at, because most times people do not build a house new with their antennas and towers and everything in place. And the electrical inspector does not tend to pop in unannounced to just check on if you added something. But if you do any work on your house or any improvements that trigger a reinspection, and you have a guy who's really looking to find something wrong, these are all little items that they can potentially, red flag you on. And more importantly, if you ever have a lightning hit and there's a fire or some damage and your insurance company gets involved, if there's anything they can pin their hat on that you didn't comply with the code, they'll use it. Okay, and the connections, again, everything refers back to any of the Article 250 sections. That's the grounding section, which gives all the requirements for, again, materials and how to terminate and so forth. Okay, for transmitting receiving installation, the antenna, conductors, and lead-in, there's a table for the minimum size of conductors based on how long it is. I'll go through this quick because you can reference all these code requirements online for free at the NFPA site. I'll give it that address in a little bit. Okay, clearances, 3 inches clear of building surface, insulating supports, unless it's in a continuous metal shield. Use a rigid, non-combustible, non-absorbent insulating material or bushing, or an opening with a 2-inch minimum clearance, or some people drill through their window pane for a pass-through. And again, the antenna discharge unit requirement is in there, but there's also an exception: the lead-in protected by a continuous metal shield, grounded with a conductor in accordance with 8.1058. An antenna discharge unit shall not be required, which is good because in many cases for amateur use, there's nothing available. Again, just the sizes are in there. Now for the transmitting equipment itself, it talks about having an enclosure. This is of more importance if anyone out there is still home brewing things, and if there's still a lot of people like, old equipment that glows when they turn it on. So there's requirements for enclosures, grounding of the controls, and interlocks if you have over 350 volts. Again, anyone running high power amplifiers and so forth, this technically could be something you'd have to comply with. Okay. NFPA, which is the National Fire Protection Association, has on their website the capability. You can sign up for a free account, and then you have access to all of the NFPA standards. And NFPA 70 is the National Electrical Code. Article 810 is primarily the one that you're looking at, and Article 250, which is grounding in general, which it's a great read, but you could spend a week going through it. Now, keep in mind the browser they give you to look through this makes it very difficult. You can cut and paste from it if you have enough diligence, but it's a great way to look things up without spending the money, the $100 and some for the standard. And you also any of the NFPA standards on there. So if you need it for you have a propane tank going in or something like that, just something to keep in mind that if you go to the NFPA.org site, they have this capability where you can sign up and get access. It's really a convenient feature. Your typical installation antennas, you have your service ground here, you have your station ground, bonded all together. Okay, I want to briefly talk about lightning protection, although again, this is something that you could take hours just to go through thoroughly. There are different kinds of so-called air terminals, lightning rods, if you will, but air terminals is the terminology they use. You have the chimney mounted air terminals, you have the copper air terminals, and you have what hams is an amateur radio station air terminal. If you live in an area that has the so-called high isochronic level, we have a lot of electrical storms, the lightning protection becomes much, much more important to you. And you want to put more effort into making it a safe installation. In the old days, people talk about zone of protection, the cone of protection, either a 30-degree angle on the cone, or if you had multiple structures there. And it's found not to be very accurate. What is used now is the so-called rolling ball method. You take a 150-foot sphere, it contacts the ground and the structure, and the area that's shaded there is considered protected. There's some science behind it, but it's really something that was derived by experimentation to come up with the strike distance. This works most of the time. This structure, if this was using the old cone of protection, you'd say, well, if you have something at the top, the whole thing's protected. And yet this corner piece here, where it got blown away by a lightning strike. So you'd have to, if you follow this, you can see where you need to have additional areas where the ball contacts, to have at each step almost, to have some kind of air terminal. The key points, remember, is ground rods should be spaced 1 to 2 times depth. And even though it's well in excess of what the code requires, you'll get the most bang for your buck. Use longer ground rods or coupled ground rods. They have ones that screw together rather than more rods. And you want to lower the ground resistance as low as possible, but not more than 25 ohms. You want to ground the antenna at the roof, the low point of the vertical cable drop, which should be at ground level, not midway, and before entering into the building. Even if you have a second story station, you more than likely want to bring your conductor, your coax, all the way down to the base of the tower, bond it there, and then bring it across and back up. Otherwise, you're going to be taking it off at the midpoint where there's only half of the total voltage drop across it, which exacerbates the problem with multiple potentials. And again, bonding and grounding of adjacent metal objects. You want to be away from gas piping, no sharp bends, everything. Again, bonding everything, all your equipment together. You want it all bonded together so there's only there's equal potential between them. And some of the polarized plugs, especially the two-bladed kind where you have a wide prong, people from trying to force it the wrong way into the receptacle, many times they widen the hole and they can go in both ways. So just something to be aware of. And you should check the integrity of your grounding and bonding often, especially for the ones that are buried in the ground. You can look online. Some of these mill handbooks have a lot of information, and a lot of it is dated, but a lot of it is good. Motorola had like a Bible for grounding. Again, remembering that they're trying to protect very, very expensive installations, so it's well beyond what most hams would use. And now we'll go to any questions. Let me, I guess, unshare it.
All right. Thanks, Don. Don't forget to unmute if you do have a question.
Just a comment. In my house, I noticed that they grounded to the cold water pipe, but I followed the cold water pipe to my pump to a plastic pipe that goes into the well. So I don't think that counts.
No, no. Yeah, that one of the problems is a lot of piping. Even if you're in an area supplied by municipal water, the piping now many times is plastic from the main into the house. So you don't have that conductive path anymore. So you really can't rely on it like you once could. You're better off with the driven electrodes, multiple driven electrodes all tied together.
It's a requirement for 2 ground rods or 2 separate sources of ground now in the code?
It would be, right now in the code, it's 2 ground rods unless you actually measure the ground resistance after putting in 1 rod, and if it's less than 25 ohms, which would be like probably $1,200 to get someone in to do that testing. So it's just cheaper to put in a second ground rod, because the ironic thing is the way it used to be written was put in a ground rod, and if it's not 25 ohms or less, put in a second ground rod, but then there was no requirement to measure it again. So especially if you're in an area with very high soil resistivity, that second ground rod may have done almost nothing, but it was still then considered compliant. So then some years back, they said, well, the typical electricity is just going to put in 2 ground rods because it's cheaper to spend 5 extra minutes than to have a guy come in to do tests and measurements. Any other?
I like that idea of the horizontal buried 2.5 feet. Here in my neck of the woods, it's guaranteed you're going to hit a rock at least every 6 inches.
Yeah, rocky areas are a problem. There are other, I didn't go into it because they're very high maintenance. There are chemical ground rods where you drive pipes into the ground, and then you have to add salts in there and keep them wet and recharge them every so often. But if you have really problematic areas, it's tough. Any other questions?
Yes, sir. Excuse me. Hang on. I'm sitting here watching and didn't have my mic out. So we should put a ground bar in our shack and run it back to the same ground that our antennas are being grounded. And by ground bar, I mean a bar behind all of our equipment and ground each and every equipment to that particular bar, which theoretically, and I know I'm going to sound stupid, but it sounds like you're inviting lightning back into the house.
No, that's not the way it works. And as I said, what you want to do is have protected devices where for any conductor that comes into the house, whether it's a gas discharge tube or a gap type device, if you, again, you can, a lot of the different mailing lists, you'll see people put very nice installations. They put a box on the outside of the house where they have all of the suppression devices. And probably the best ones are the ones that have replaceable elements. So if you do take a hit, you can replace it easily. But to get back to your specifics, yeah, you'd want to have like a ground bus in the station, and all the equipment that's in that station, including if you have computers, printers, and so forth that are interconnected, would get connected to that ground bus, each with their own connection, not daisy chain, like from one chassis to the other to the other to the ground bar. And then that ground bar could either go to say a station ground outside your window, and then that gets bonded to your service ground, or it could go right to the service ground if it's close by, using one of those intersystem bonding devices.
So if I guess either way would be equal for me, but if I went out of the room and I went outside the window and then down to the grounding rod that I've got driven in, well, 7 feet, obviously not 8 because it's still sticking up, and I've learned that tonight. Or I could just take it out, run it alongside the wall, and then basically hook it into the electric panel, the fuse box?
Yeah, theoretically, you could do that, but it's with that amount of a run, you're probably better off putting an electrode in the ground underneath your window and then bonding that, run the bonding conductor around to the other ground electrode to bond them together. Ideally, if you can, bury it in the ground, it gives you a little more electrode effectiveness, but you don't have to. Just if it's above the ground along the house or something, you'd have to provide mechanical protection if it's in an area where people could snag it or run into it or something like that.
Okay, thank you very much.
You're
Now, it was an interesting presentation. I really do appreciate it, sir.
Okay, thank you. Yeah, it's, as I said, this, I used to do we did like 2 to 3 3-hour classes and just on grounding. And I've been trying to condense it down for the amateur presentations to eliminate a lot of the grounding stuff that, because it's Article 250 in the code. And if anyone enjoys reading codes and standards, it's quite an interesting section. And as I said, it's the largest section of the National Electrical Code because they do understand grounding is a very important thing.
Again, thank you very much for your time on this. I do appreciate it.
You're
We
quite
all
welcome.
do, actually.
Quite welcome.
Well, I have a question.
Sure.
In one of your slides that you showed what the code says about not requiring insulation on a conductor for grounding or bonding.
Correct.
I remember reading someplace, I can't remember where, that it's best to use uninsulated conductors for grounding because of the differential C factor between insulated copper and bare copper, at least for amateur applications. Does that make any sense to you?
Well, as far as, for RF, it's one thing, but although if you take a lightning hit, it's basically a high frequency occurrence, a very short but high rise time non-DC event. But it's for grounding purposes and bonding purposes, uninsulated is fine. And again, if you have it outside and it's visible, you may not want to have it too obvious that it's copper. But again, I don't know if maybe downstate here we have more thievery going on, but copper is hard to hold on to sometimes.
Okay, thanks.
Okay. Any more questions? Must be some questions.
Oh, I just have a comment. I installed those coax grounds that have the little fuse in them. I forgot who they're made by, but I put them on a connector right to the ground rod that plugs one end of the coax into the continued end of the rest of the coax. I don't know if you want to touch upon that.
Yeah, you can do that. Just remember that ground rod then, if that's your station ground, should be bonded to the service ground. The bonding of your ground system is extremely important to create this equal potential condition where you don't have two different so-called ground potentials between your service, again, which you have in your station by virtue of that green wire. And if you create another potential that's coming in on your coax, the potential there is for damage to the equipment. And even, many times it doesn't even have to be a lightning hit. If you have a nearby electrical storm, you can have a lot of inductive pickup in antennas, especially big dipoles and things. And although the energy in that is not very much, as far as doing damage. If it causes a breakdown, because it could be thousands of volts, many thousands of volts, and if it causes a breakdown inside your equipment, which is adjacent to, say, your power connections, the ionized air or gases from that arc could create a path for the power current to follow through and create a problem. Just as an example, when I first got into amateur radio, I was in high school, and I had less than the ideal setup. I was on the second floor of a house, and I I used to almost religiously disconnect and ground all my coax connectors before I would walk away from it after using it. And one night, apparently, I disconnected the antenna, and maybe I was in a hurry to eat dinner or something, and I just left it laying on the desk. But lo and behold, about 3 o'clock in the morning, I woke up hearing crackling sounds, and I looked over, and there's arcing between the shell and the center conductor, the coax. You know, and if you look at how much voltage you need to jump across there, that was probably about 5,000 or 6,000 volts just from a nearby electrical storm that was being inductively picked up by the antenna and then coming down the coax. So it doesn't do any damage in itself, but it can cause other breakdowns that can be damaging.
So you're saying I should probably bond my ground for my radio's separate ground rod and my coax to the panel of the house or to the ground rod of the panel, or does it matter? Same thing.
It would be preferable to have it connected to the ground electrode conductor that goes to the ground rod for the house. If you have a ground rod for your house.
I got to go find it.
Yeah, and if you don't, and depending on your house was built, it may not, especially if they used a water pipe or something. It's best to add it to have it and bring that back to the panel, and then bond to the with that intersystem bonding device. You can tie onto the ground electrode conductor, and then anything else, whether you have cable TV or satellite or phone or anything else coming in, you can bond them all together there.
One other question. I want to put up a telescopic tower that also tilts. It's got a hinged base. Is there some sort of a flexible wire? I don't want to bend a number 6 many times and have a problem with that. Like the conduit that's flexible for when you hook up an air conditioner unit on a concrete pad and it moves. I know they've got flexible conduit. Or maybe I should put the ground.
Where people have a problem with where there's a connection has to be made, and many times you see this on fence gates. They will use a braided conductor, and again, the braided conductors they require a little more checking every so often to make sure there's no corrosion building up or any damage to it, because as the individual fine conductors of that braid start to break and stuff, then you can have like micro arcing if there's a fault, and then it melts back. But a flexible braid, and I mean, you can buy them, but the terminal is already crimped on, but it should be a gas tight crimp, can be used. And does your tower tilt at the base or up like 6 or 7 feet?
No, I'm going to make it so it tilts on a hinge at the base, at the concrete base.
Okay, then a flexible braided conductor, preferably say at least 2, so you have some redundancy there, would be something you could use that would be able to accommodate the movement and not be damaging itself.
Does a braided cable come in a number 6 or any sort of size? I'm curious.
Yeah, what it'll be is it'll be specified by the circular mills in the braid, and you can just, if you look up a table of conductors, as long as it's the same or more than the circular mills for a number 6, then you're fine.
Oh, that's right, because it's multiple copper pieces. So the circular mill will probably have more because there's more cables in a smaller size.
It's more compact, so you're gonna get more copper in there than I say it's you actually probably want to go a little larger, only because, as I said, there will be some damage over that you may incur as it ages and gets flexed. Depends how often you're going to let the tower down too. If it's only going to be once in a while, the braid's going to last a long time. If you're doing it regularly, then probably every time you do it, you do a once over inspection, make sure the braid looks like it's still intact.
Yeah, I don't know how often I'm going to tilt it over, A, to change the antenna, but B, I might freak out on my lightning app when I start seeing lightning and just bring it down to the ground and lay it on the ground. The smallest is about 28 feet or so.
Yeah.
It goes up to
something to keep in mind. Although everyone feels comfortable that the high point is going to be the part that lightning hits, it doesn't always happen though. Lightning will go where it wants to go. It's I didn't include them in this. I had some slides from another presentation with a friend of mine who his mother's house, which was surrounded by tall trees and other houses that were bigger. It was a little ranch. Took a lightning hit, went right through the roof, blew a hole through the roof down into the kitchen, wiped out, telephones, fax machines, all kinds of stuff. So it doesn't always have to be the high point. There are some really great photos of lightning strikes, a third of the way down to the Empire State Building. So, and most people would think, well, it's going to hit the top of the antennas first. It goes where it wants to go. And it's largely based on if there's contaminants in the air that create a better ionized path, if there's some other, forces at work. So lowering it down, it's probably better, but it's not a guarantee. You still should keep all your connections and protections in place. I hope that answered the question.
Yeah.
Okay.
Don, I have a quick question, if you don't mind.
Sure.
It's actually a question I have to relay from somebody who doesn't have a microphone in the ask in the chat. Did I see somewhere along the line that it is possible to mount or to install your ground electrodes in a horizontal fashion, so you cannot get them into the ground any more than, say, about 3 feet? Is that an acceptable enough ground for usage?
If you dig a trench 2.5 feet down at least, and certainly 3 feet would be fine, and lay the ground rod horizontally in the trench and bring your ground electrode conductor up, that would be considered acceptable.
And would you suggest multiple ground rods in that type of situation, given that it's a less than ideal depth?
Well, the more the merrier, but just remember, you don't want them too close to each other. You want to separate them. Again, at least 6 feet per the code, but 16 feet would be best for 8-foot ground rods between the ground rods.
Okay. And one further question before I let anybody else take over. You were talking about, with Bob there, you were talking about braided connections. In the old days, they used to have these braided ground straps that they used to use on tractors and old cars. Would something like that be an acceptable device for use in a high bend situation or motion situation?
Well, the braids, I can remember a lot of times older cars, and also like a lot of times pickup trucks, but the bond the bed to the chassis, the frame, would use braid. The problem is the terminations for that are probably not as good as you want. You want something that's and typically, like I said, like a solid gas tight hex crimp terminal. So there's no empty spaces in there. Or you could use a brazed connection, something like that.
Okay. I kind of figured that was going to be the answer, but wanted to ask. Well, thank you very much, Don. I'll go quiet now.
Okay.
Sir, one other question that just popped into mind. Like you said years ago when you had left, most of us run when we hear a thunderstorm and we disconnect our antenna leads into the house. And that, of course, sometimes we can't do it at the window, so we do it inside the shack. And then we leave that coax just hanging. I don't know, should that somehow be screwed into something that's grounded to that ground bar?
Yes, yes. And either, I mean, some of the antenna switches have a position that will connect everything to a ground connection. Or you can just make up your own. You get a bunch of SO239s and mount them to a plate and screw them into that. You know, have them bridge together the center conductors and the shell. If you have any place that sells a lot of military stuff, the Army used to have a connector that basically would screw. There was a male coaxial connector, but it tied the center conductor and the shell together, and then had a little set screw in the end where you could put like a ground wire, a bonding wire. I've never seen them commercially for sale, but I used to see them when I was in the National Guard. We had them.
I thank you. And believe me, it's like when you're unscrewing 5 antennas at the window every time, especially lately, boy, it gets to be a pain. You kind of wish you had some kind of snap-on thing like the hydraulic, the hydraulic hoses where you pull it back and
Yeah,
snaps on.
yeah, the quick disconnection.
Yes.
Yeah, you could, and again, hams are known for being extremely frugal. We spend a lot of money on equipment, but sometimes we chintz up on other things. If you have multiple antennas that you just want to be able to disconnect, you could always, put an antenna switch, just a 2-position switch where the other one went to, a bonding connection or a ground connection. And then you can just flip switches.
I like that. Yes.
Yeah.
Thank you very much again.
You're welcome.
I was going to say Alpha Delta sells a really good switch that has lightning protection built into it. So that's something I use in the shack.
Yeah, and the nice thing about that is you're more inclined to, ground things when you should, because it doesn't take as much effort.
And there's also lightning protection that goes in line between your antenna and the actual shack. You can get something like that as well.
Yeah. Again, remember the preferable point to have your initial protection is before the coax enters the house. The whole idea with protecting against lightning and things like that is you want to deflect it, so to speak, so it doesn't enter the house, and provide a path for it to go someplace else. So by having a grounding and bonding connection outside before the cable comes into the house, you accomplish both of those if you use a protective device. So this way it short circuits the signal, the impulse coming in, and it provides a path for it to go to, so you can control where it goes. Otherwise, it's going to find another path. It's electricity is funny that way.
Hello, I got one quick question for you.
Sure.
Jim, K2BHM. Just curious, in your professional career, did you ever bump into a fellow by the name of Vince Idone, Atmospheric Science Research Center, SUNY Albany?
No, I did not.
He did a lot of research on lightning and did a lot of recording of it. I did a lot of work for him, setting up equipment for him and stuff like that. They had a special facility down in Florida, a lightning lab, and they would actually go and trigger lightning and measure it.
They shoot
and document
rockets.
it and so forth.
They shoot rockets up sometimes with the,
Yeah, they shoot the ground rod up into clouds,
yeah. Yeah,
they-
go ahead.
and they would photograph it. The cameras, 16 millimeter motion picture cameras. Normally, a 50-foot reel would go through your projector at 2.5 minutes. This would go through 500 feet in 2.5 seconds. They were shooting like 10,000 frames a second.
Oh God, this is getting more complicated.
Yeah, that's an interesting field. There was a number of people who they basically their whole life has been devoted to lightning and its effects and protection. And I mean, we're fortunate in this country because, with the exception of Florida, the isochronic level is not all that high. The rest of the country, but there are other countries where it's a routine thing for multiple fatalities from lightning. People are out on a soccer field or they're in a little shack or something and they get wiped out by lightning. It's quite a problem in certain areas.
Yeah, he did a lot of research on that, and then I got involved when he was starting to document the ultraviolet portions of the lightning bolts. And then I retired. Thank you. Excellent
Retirement's
presentation tonight.
Okay, thank you. Retirement's fun.
Oh, I'm busier now than I ever was.
I know. I found the same thing.
My dad told me that once he was retired, he doesn't know how he ever had time for work.
Yeah, I didn't understand my dad saying that either until I retired.
Yeah.
Don, I was just wondering, have you ever seen one of the lightning demonstrations, like the large-scale Van de Graaff at the Boston Museum of Science?
I haven't seen it there, no.
Definitely worth a trip.
Yeah.
They do gear it towards the youngins a bit, but it's fascinating, and I do like the way that they do it. They have a pretty good sized chamber, like the size of a planetarium.
Mhm.
And the guy who runs it sometimes is within a giant bird cage just to demonstrate how things travel on the outside.
Yeah. Well, it's funny. Some years ago, when I was with an electric utility, I had to go to Muncie, Indiana, to the then Westinghouse large power transformer factory for impulse testing of a transformer. And they had I'm sure whoever first built this thing probably was a ham. It was definitely like a kludged together apparatus for generating high voltage, and it was inside, but it was unenclosed. You know, they had a fence around it, and you know the problem was after about 2 o'clock in the morning, the pollen was so heavy in the air there would come in. It would start to break down an arc within the device. You know, because there's a big, it was probably like 30, 40 feet tall. They had with all insulated conductors and things. And it was funny, the thing would just start to break down and then you'd call it quits and stop testing for the day. So that was the only real demonstration I had of something like that. But yeah, I have to look into that. It'd be lighting is fascinating, scary something. You know, you go through stages when you're a little kid, you're absolutely afraid of lightning. It scares the daylights out every time you hear it. Then you get to a point a little older, you say, well, you know, everybody, these are the experts, they know, the utilities know what to do and everything else. And you don't worry about it. And then when I worked for utility, and one of the things I was involved with was developing a substation grounding standard, I started getting worried again. Because there's a lot that we don't know. And there's a lot that you know, that gets overlooked. And I said, the grounding is very important. And what people don't realize is if you have like with especially the utilities, a ground fault, with a high current ground fault, the mechanical forces that are generated in the conductors are tremendous. So like I've seen people where they'll have an undersized ground electrode conductor attached to a tower leg with a hose clamp, and if that really took a hit, it would just blow itself to pieces right off the tower. And the tremendous forces involved mechanically from the reactions, the magnetic reactions.
One more comment.
Sure.
That's why you hear the loud banging when you're in an MRI getting your scan done.
Yeah.
They put some pretty intense currents through there to provide a gradient to the magnetic field.
Yeah.
And when you get that much current in a magnetic field, it moves.
Yep.
And that's the banging.
Magnetism is fun,
I'm going back to ignorance is bliss. Too much knowledge is scary.
So yeah, I definitely recommend if anybody's up in the Boston area, taking a trip to the Science Center and watching that show. It's certainly worth a look. I also want to mention real quick, if you're interested in the radio aspect of atmospheric discharges, there are things called spherics, tweaks, and whistlers. And spherics is spelled S-F-E-R-I-C-S. Spherics, which is, I believe, like a contraction of atmospherics, is where that came from. But spherics, tweaks, and whistlers at the VLF end of the spectrum, all the way down at the bottom, you can kind of listen to our atmosphere when there's electrical storms, and doesn't always sound like what you would expect, which is why one of those sounds is referred to as a whistler. So if anybody wants to experiment with something like that, there are receivers you can build, and you can take a listen to it. It's interesting stuff. So I want to thank Don for coming tonight for our first in a series of Tuesday night presentations, and thank Dave, our president, for helping us get this going. And we had a really good turnout tonight. Really happy with that, and hope to continue this series of presentations. Everybody unmute, please, if you can, and give a round of applause for Don.
Again, thank you very much, sir.
Thank you. You're a good audience.
Thank you. Very
Thanks,
informative.
Don. And
Okay.
at some point, I'll see you down there again, I'm sure.
Okay. Okay.
Thank you very much for me as well, Don. Very much
Okay.
appreciated.
Everyone have a great night.
Thanks. You too. Good night, all.
Night.
Good night.